Very good. We can try to solve the task of today's lecture. What was the first? It's a Poisson ideal. Let's try to understand the question and to solve the problem. Let us illustrate it for n equal 3. What is this ideal for n equal 3? E1 3, yes. There is one element, but the ideal generated by E1 3 means that it is a function, just the generic function multiplied by E1 3. Okay?
Some function from what?
F is a function from S of B plus. We generate an ideal by this function. So we can multiply this function by all functions. But then we consider the zero of this ideal, the zero set of all elements of this ideal. And it is exactly the space of three diagonal symmetric matrices: E11, E22, E33, E12, E12, E23, E23. But here we have zero because we consider the zero set of all functions from this ideal. Why it's a Poisson ideal? Why all functions, the Poisson bracket of all functions like this, are again function of this type?
In fact, we have only two elements to check, U1 and U3. The other are all zero. Because the bracket, they have to be current set, which has least one, the index.
So we have to verify, but I don't understand what to verify. What you need to verify?
Just to verify the Poisson bracket of all other elements are still in the form of some function multiply U.
Would you like to try? And 1, 1. No, it's 1, 3. It's minus 1, 3. You remember the Cartan element acts else always diagonally. You see? All generators are the eigenvectors for the action of the Cartan element. EII, commutator with EKL, is always something EKL with a constant. So this vector is always an eigenvector for the action, for the adjoint action of the Cartan element. It's an adjoint action of the Lie algebra.
So as I understand, we need to show that the Poisson bracket with other elements are 0, right?
No,
Or what is showing there?
but they should be expressed in terms of the same element.
Okay.
You see?
Okay, no, okay.
But they should be 0, then restricting to the 0 set of this ideal. So your statement that only such Poisson bracket are non-trivial, and both of them are expressed in terms of the same element. So they are in this ideal. Very good. Could we do the same calculation in general now? I have a simplification for you. So we suppose that is less or equal to G. So it's a general element. And this element is from the ideal. And K is less G minus 1. What is the commutator? I'm sorry, L.
Not zero, it means either or, and if you want J equals to K, it means
Absolutely.
and it is what
Yeah.
we require.
Yeah.
And otherwise, if you require I equals to L,
Why J is greater than I? Oh, yes, okay, of course, yes.
so it's also inside this.
Mm-hmm.
So it is.
I agree. Okay, it means that it is a Poisson ideal. Is it true if we place here some K, some S greater or equal to 1? Should it be the same? So could we take several diagonals starting from the K diagonal? You understand?
Yes.
I think it will be the same.
Just change.
Yeah. So it means that if we fix here S, then this is also a Poisson ideal. Very good. Let us now discuss the second home problem. It considers the problem of the center of the field of fraction of B plus, of S of B plus. But maybe firstly, I propose to you to verify the statement for nilpotent. So you remember that S, the center of S of n plus is generated by delta k of L for k greater than n over 2. Let us verify it for n equal 4. In this case, free six-dimensional Lisa-Bell algebra.
N equals 4, only one guy remember, because at least his k is at least 3. Yes.
There are two elements. And what are the elements? Okay.
1, 2, 3, 4.
For k equal 2 and for k equal 3. For this one, it is
1,
1, 4. Yeah. Is it obvious that this is the central element for the nilpotent Lie subalgebra?
What was our base of nilpotent?
Base? For S nilpotent n plus Eij for E lesser equal to J. Strongly up triangle. Mm-hmm.
So it's all 0.
It is 0, yes, because there is no such elements. So it's obviously central, and for k equal 2, what is the element?
Delta 1, 2, 3, 4.
1, 2, 3, 4. And it is E 1, 3, E 2, 4 minus E 1, 4, E 2, 3. Let us verify some commutators. Which commutator is not evident. So, for example, E23 is evident, but what is not evident? For example, E34 is not evident.
And D1, 2.
Sorry?
1,
2. E12. So yes, this is evident. There is no such indices, but is it evident the commutators with these generators? Please verify. Is it clear? Mm-hmm. If done, please start thinking about the question of the Barrel-Lisa algebra. What is the difference if some generators from the nilpotent Lisa algebra suits the Borel one?
I guess it's still delta metric, but may have some dominator.
Mm-hmm. So you see, for example, this generator, it is also in B plus, because n plus is the Lisa algebra, and it commutes with all nilpotent part, but does not commute with the Cartan part. So what to do? Yes, we have considered some ratios. Let us else consider the n equal 4. There should be two central elements for n equal 4. Central element for the Barrel in the field of fraction of Barrel.
For n equal 2.
N equal 4. For n equal 4. And one is obvious. Could you find one central element for the barrel?
Obviously, like trivial or something.
Like?
A trivial element for.
For n equal 4. It is for generic n, but so one element in the center is can be guessed simple, just by some obvious reasons. The trace of the matrix. Because the trace of the matrix is a central element in GLN, and it is an element of the Barré-Lissab algebra. You see, this is the idea, the general idea, to find something central one, but which lies in the Barré-Lissab algebra. N equal 4. 1 is just a trace of the E11. So it's a central element in this, but another one is not tricky, and so it is explained in the context of the Todd system. So it is really related with the construction of Todd Hamiltonians. Please.
Now we have double bases, right?
Double
Bases, because we have non-dominating.
double bases.
Yes.
What does it mean? What do you mean?
We now have like 1 divide E1, 1 divide E1.
Yes. I will simplify your research. So it's a ratio function f on E14.
I guess that delta.
Delta?
Yes.
Which one?
1, 2, 3.
No.
So E14 is the central element of nilpotent. So we had
Yeah.
for
Yes.
n equals 4.
Yes. But for the barrel, it's not a central element.
Yeah.
An idea. This is delta 1, 2, 3, 4, E14. So it's not right, but can we verify it? You can calculate the commutator. Please verify it is not 0.
So is it possible that if we take a general matrix of B plus, and if we do the chopping procedure we did in the class before,
Yes.
the two dimension matrices elements that you had in the class before, we saw that this was a Casimir element for this case, and maybe for this case also is a Casimir element.
Yes.
It's the same.
Yes. That's right. But could you write it? Could you write it?
Right. Then you should write the same expression.
It's a very good idea. Please.
So we are trying to find the central element for. Is it for B plus or for N plus?
B plus.
B plus.
Uh-huh.
Okay, and the basis we are taking for B plus is B plus are upper diagonal matrices.
Diagonal and upper diagonal.
Yeah, we consider also the diagonal.
Yes.
Yeah.
So it's
I,
less or equal.
Less equal than
Yeah.
So for n equals 4, we should have something like 1, 1, 1, 2, 2, 3, 4. So if we if we do the shopping procedure for we could do this.
Mm-hmm.
So, but this is not maybe a good idea because
Oh, no.
the only thing we have left is this determinant for the two-order matrix.
So it's better to write all the elements.
Yeah.
1, 4, 2, 4, 3, 4, minus lambda, yes?
Yeah.
Mm. Maybe it's a good time to write this polynomial, this partial characteristic polynomial, the coefficients.
So now I have to consider all possible combinations of the determinant of two matrices. You see?
Yeah.
The minors.
Yep. I don't really understand what you do.
Okay. So when we do the chopping procedure, we have to compute all the determinants.
So I propose to you just to write all this function on lambda. So the determinant of this 3 by 3 matrix.
Yeah.
Do you remember its decomposition on powers of lambda? There's lambda square.
Yeah, well, we can.
Lambda square multiplied by what? No. 1, 4. Lambda square multiplied by E14.
You mean the final decomposition?
Yes.
No, I don't remember the entire form. No, but I can just do 1, 2, 3, 4, and then 1, 2.
Free 2, we have no free 2. We have only
No,
free 4.
3, 4.
1,
4.
Mhm.
43.
Yep. One, four.
1, 3, 2, 4.
Mhm.
And last one. So, 2 to 4 to 6.
Mhm.
This is the terminal.
Very good. Uh-huh.
So now we do all the problem and obtain the terms of the composition.
It is very instructive to extend it on lambda.
Yeah, because,
Expand.
then when we have the highest order lambda, we have to divide in order to obtain that term.
Yeah, yeah.
Well, from this we know that it should be 1/4 the coefficient of the highest order. Yeah, well, it's the same that we did for the 3-order matrices in the previous class, but in that case it was only a 2 times 2 matrix. So
The highest second order will be only from this expression, and this will be multiplied by E14.
yeah. So minus minus will be
Lambda square E14. Uh-huh. Very good.
so now 4, 3, 3. I don't know if it is necessary to obtain the linear terms. I can do maybe just the.
As you like. There is some technique I will show you.
Okay. So maybe I will omit these terms and will only consider the linear terms, the left linear terms, because this is the term I want for.
Okay, but
So maybe this I will omit.
it's better to write it down, because you will see why
Okay.
why it is the central element. Mm-hmm. Plus E14, E22. Mm-hmm.
And the other one is 0. And from here we have.
Mm-hmm. Minus. Uh-huh. 1, 3, 3, 3, 3, 4. Uh-huh. And also minus 1, 1, 2, 2, 4. Very good. It is a determinant. You know that at lambda power 0, you have just the determinant of all these metrics.
Yeah.
So here you have just 2, 3, 4, 1, 2, 3.
Okay.
Okay. So f should be this element, and we have to decide why. We have to understand why the ratio of two such elements is the central function in the barrel.
For 3,
Yes.
we do in the previous class, it was the last term.
No.
You see? No,
No.
it was the linear.
The ratio of such two functions. But first of all, there is a good formula for this expression. It is E delta 3, 4, 1, 3 plus delta 1 plus delta 2, 3, 2, 4, 2, 4, 1, 2. Do you agree? Plus. So all this expression is the sum of minors.
So this minor is?
3, 4, it's the line 3 and 4. And these are columns, first and third.
Okay.
And it is because you choose this lambda and find this minor.
Yeah.
And then you choose this lambda, extract this line in this column, and consider this 2 by 2 minor. So it's a rapid way to calculate the same expression. What do we know about the coefficients of this partial characteristic polynomial given by the chopping procedure? What is the theorem? How we apply the Adler-Kosten-Syme scheme to this case? We know that they are in involution, and we know that they are B plus invariant. It's a theorem. Okay?
Yeah, but not always the coefficients are Casimir functions. In this case, this is Casimir function, but they are not always Casimir functions.
Yes, why they are Casimir functions? We know that they are B plus invariant functions.
Yeah, but sometimes these coefficients are not Casimir functions.
No, only the ratio.
Yeah, only the ratio.
So we need to write the complete non-symmetric. You see, we calculate such chopping determinant, and we consider two such coefficients, and one of them is this, and the second is given by additional minors to this element, to algebraic complement to these elements in this matrix. My statement is that these minors are element of the nilpotent subalgebra. They expressed, so then you consider such the algebraic complement to this element. You extract these elements, so you consider only such elements. It does not take this element which is not in the Borel-Lie subalgebra. You construct such a function with only generators from a Borel-Lie subalgebra. Is it approximately clear? So my statement is that this coefficient and these coefficients are elements of S B plus, both of them. And we know that before the reduction, before taking the symmetric part, the ratio of such element is B plus invariant. And both of them are element of S of B plus. It means that the ratio is a central element in B plus. So if you consider this element, It is not in B plus. It has these coefficients. Okay. The ratio is also invariant. So delta 2, 3, 4, 1, 2, 3 divided by E1, 4 is also invariant. But it is not an element of B plus. And after reduction, it produced something non-trivial. But this ratio, it is before reduction. It is an element of this symmetric algebra constructed just from B plus. I don't know. Let us verify. So let us verify in n equal 4 that this ratio commute with what? With E2, 2 and E1, 3. Have you copied it? Yes? Have you succeeded?
No.
Would you like to try? We will help you. Okay. So this is F. We can see the ratio of F and E1, 4.
Okay.
E1, 4. And we would like to calculate the Poisson bracket with E2, 2, for example.
Yeah. So using linearity for possibilities here.
Mm-hmm.
The first one here cancels. For the other ones, we can use relation, which is so for the first one, we have this is the other.
Yes.
Here we can use Leibniz rule.
Mm-hmm.
And so, for example, we can consider this as an operator.
Yeah.
And
Yeah.
we can write it on the front, for example, 1. And here, yes, we have. And the same here. So. here we can use again the Leibniz rule.
Okay, you missed here 1 over E14.
I put it in the same bracket. Ah, yeah, wait. No, you're right, because there are these other terms. So, here, with all minuses. So, and -1. Okay, well here, no.
And here.
Here.
Mm.
1, 4.
Mhm.
Okay, that's fine. So, the first term we use here. This cancels.
Mhm.
So there is the other one, which is
Cancels 2.
cancel as well. So here is gone. For this, we use instead the fact that if we consider some bracket between of this 4, this will be minus square of this.
Very good. Yeah.
Okay.
Yeah.
And so in this case, we will have plus square E14. And again here cancels.
Yes.
And so this one, after we have this other term which instead does not cancel because of E12.
Mm-hmm.
So we have -1 here. So for this term, instead we have e to 4. So this is equal to e to 4
Mm-hmm.
minus and just e to 4.
Mm-hmm.
So here we cancel. And for this other term, we have instead the minus 1, 2. So this is one term.
Yes.
And the last one, using again this expression, it is 0.
Yes.
I would say. So this is the last term.
And it is also 0.
And yeah. So this is equal to 0. And they commit.
Very good. Could you calculate the... What do you think is interesting? With which generator? Which Poisson bracket is not trivial? Could be not trivial? 2, 2. Let's calculate 1, 2. E1, 2 with the same,
okay.
yes.
So now, in this case, for the first one, there is commutation.
Mm-hmm.
So we have E12, E22, which is instead trivial. And so we have the E12, just E12.
with this.
Yes,
Uh-huh.
yes, and that's it. And
This
there is
is-
no other term.
And this.
Now
oh,
these are these others.
Uh-huh.
Yeah, as well.
and-
And now we have the last term, which so we have 3, 1, 2, 3, 1, 2, 3, 4, 3, 1, 4. Okay, this one is 3, 1, 2, 54.
Yeah.
And the other term, which is minus,
Other term, which one?
because I use the Leibniz rule, I put
Yes.
this outside, and
Yes,
I
yes.
need to put on the other side, so it would be 4.
But it's 0
Yep. I was-
because the
yeah, yeah.
Poisson bracket. Yeah.
So, yeah, okay. Here we have 1, 4, 3, 1, 4, and the other classes. So this is 1, and this is 0 again.
Yes. Yes. So our theorem is verified in this simple case. Thank you very much. What is your name?
John Luigi.
Nice to meet you. Okay, let me try to demonstrate the theorem in full generality. And let us recall the AKS scheme once again. So let L be the full GLN N1 E and N. When we calculate delta K of lambda, we remember minus lambda E minus lambda E K of L. We consider such a corner, determinant of L minus lambda E K. And then we extract it in powers of lambda n minus 2k E K n minus 2k lambda n minus 2k minus 1 E K n minus 2k minus 1 lambda 0 K 0. So let me remind that E K I, all this family is a commutative family in S of GLN. Okay. And the second point was that Ki divided by Ek0 Kj for all I and j 1 n minus 2k are B plus invariance. So this was the points why we can apply the Adler-Kosten-Syme scheme. So we can restrict these functions to the Borel part. And the Adler-Kosten-Syme scheme says that the restrictions of these functions to the symmetric matrices will be in involution. But before this restriction, we can see that Ek n minus 2k minus 1 divided k n minus 2k are elements of S of B plus. and combining this with the point 2, and 3 means that these functions are in the center of this Poisson algebra. So let us verify this. And maybe firstly, I'd like to say what is this function for k equal 0. What is this function? Sorry? No, it's a trace. Because we consider the highest term at lambda and the sub-highest term, it is exactly the trace. Trace divided by 1. So it's the trace of L divided by 1. It's a trace. Okay? But why it is true for all k? For all k. How it is organized? I need I need more elements. E1 1, then E2 2 minus lambda, En minus 1, n minus 1 minus lambda, En minus lambda, and then I make such a chopping. I consider this determinant the highest term in lambda. If we choose all lambda on the diagonal, it is just this minor. So k n minus 2k is just the determinant 1k n minus k plus 1 n. Inversely. No, it's okay. 1k, and the columns are n minus k plus 1 n. So the highest term at the highest power of lambda means that we have chosen all lambdas on the diagonal, and it means that they subtracted all these lines and all these columns. We multiply this product of lambda only by the determinant of this corner. Okay? And it is obviously an element of S of B plus. It contains elements only from B plus. Okay? The highest element in this decomposition, this term, how it is obtained. We take not all lambdas from the diagonals, but all except one. Okay? For example, if we have taken all lambdas from this diagonal, but not this one, we subtracted all lines and all columns. And lines and columns. And it means that we can take from this block only this element. Okay? And we multiply it by what? So we multiply these lambdas by by this minor. Okay? But this minors also contains element only from the Borel-Lissab algebra. It take one element from the Cartan, but no elements from the lower diagonal, lower triangular part. Never. And it concerns all the diagonal elements here. So if you take n lambda from here, but omitted some element here, you consider such a minor. So you always consider minors of such type, which are of the dimension k plus 1. They touch some element from the diagonal, but never take the element of a lower triangular part. And it is already not true if we consider next element. It always contains something from the lower triangular nilpotent part. But this ratio is always an element from this field of fraction of the Borel-Lissab algebra. And it means that, so from the AKS, we get that all the ratios are B plus invariant functions, but the ratio of two principal terms in all these polynomials are always an element of the field of fraction of the Borel-Lie algebra, and it means that they are central inside this algebra. And that's why these coefficients are Casimir functions for the Toda system. They are trivial functions. They are constant for the physical model. They commute with all Hamiltonian vector fields on this space. Okay, very good. Let me remind you the question of R matrix Poisson structures. Do you remember? So, if you remember, we started to work with the Toda, the open Toda chain with the, I'm sorry, just by its Lax representation. So it was for us a manifestation of its integrability, and firstly, by the argument that all functions, all spectral invariants of the Lax operator are integrals of motion. But the involutivity was not a direct consequence of the Lax representation. So we used another technique, which was the R matrix RL1. Okay. And there was also a home task. I'd like you to recall it for the next Monday. That there is such a Poisson bracket with R, which is sum of Eij for I less than j minus Eij. So the home task to verify this formula with such an R matrix. Yes. And this formula was now sufficient. Was sufficient to demonstrate that one shows that K are in involution. we'll consider a generalization of this approach. I suppose you remember that for L, just the GLN Lux operator. The standard Poisson structure GLN was expressed by the permutation operator with L2, which is also called P L1, or 1 over 2 P L2 minus L1. There, P is the permutation operator for all Ng. So if you don't remember this, it is the home task 4 to verify that for GLN Lux operator such formula holds. And you see that there are, in some situation, we have the formula with plus. In some situation, we have formulas with minus. And your home task 5 will be to verify if the Poisson bracket has the form R1 L1 plus R2 L2, so with even with some different R matrices multiplied commutator of different R matrices with the first and second tensor copy of the Lux operator, then we have that the spectral invariants are in involution. Okay, we will start by this next time. We finish for today. Good continuation.